Hi everyone and welcome to this new video. In this video I want to talk about the difference between a 32-bit application and a 64-bit application in the context of binary exploitation. Now specifically the difference we are interested in for the purpose of this video is the calling convention, and we will analyze with two practical examples that the calling convention used in 32-bit applications is different than the one used in 64-bit application. Now, what is exactly the calling convention? Essentially, it is the way that like a language, a program implements function calling. That is, if I have an executable in the context of Linux, which is an elf file, I start from the main function, but of course from the main I call different function. I can call the f function, I can call the g function, and so on and so forth. Now, when I write a program in C, I just do function calling with the name of the function and the parentheses. Eventually, I can pass some arguments too. However, when this thing is actually compiled into an elf binary, this function calling is actually implemented in different ways. If I have a 32-bit application, it's going to be implemented using the stack. If I have a 64, it's going to be implemented using the registers. And in this video, I just want to analyze this kind of thing. As always, I hope the video will be interesting and enjoyable. If it is, leave some feedback, subscribe to the channel, share this video and this channel with like-minded people to help me grow. Thank you very much and enjoy the video. So, we want to analyze the calling conversion. Perfect. However, before doing that, we need to talk about the instruction set architecture, which is often abbreviated as ISA. So, what is the instruction set architecture? Well, the instruction set architecture, ISA, defines the abstraction layer between the hardware and the software in our machine. Now, specifically, it defines the following things. It defines the set of instructions that the CPU can execute. These are the instructions that we actually see in the elf binary. When we compile something from a .c to a .exe or a .elf in the context of Linux, I mean, in Linux you don't really have .elf, however you still have elf binaries. So when we compile something into elf, this thing will have all the data and all the instruction required to be executable to execute. Now the instruction will use a specific format, a specific set of instruction, and this set is taken from the ISA. This means that the move instruction, the ret instruction, all this, the push instruction, the pop instruction, all the assembly instruction are defined in the ISA, and the ISA defines this set of instructions. Different ISAs will define different sets of instructions. It also specifies how the processor interacts with memory and input-output. It establishes how processor handles control flow exception and interrupts, and in general, it acts as the interface between software and hardware. And this is the main point to understand. What is an ISA? It is an interface that abstracts away the hardware. The point is that I don't need to understand exactly how the hardware is implemented. The only thing that I need to understand is what the hardware gives me. So the amount of memory it gives me, the amount of instruction and the different types of instruction it gives me. And in general, the interaction between software and hardware is governed by the ISA. It is defined by the ISA as the set of all possible things I can do with the underlying machine. Now, why do we even implement an ISA? Why does it even exist? Well, the main idea is that since it abstracts away the hardware, once we write the software for a specific ISA, we can run it on different hardware processors as long as those implement the same ISA. So the idea is that think of like object-oriented interfaces. Well, the idea is that I have this interface, right? The implementation of this interface can be different. I can have, CPU 1, CPU 2, like there can be many different ways of implementing the same interface. But the idea for the software that uses the interface is that as long as the interface is not touched, as long as the interface is the same, this software can run on all this hardware. And in general, that's a very powerful concept of computer science. It is the concept of abstraction. Abstraction is not magic, it's just a lot of engineering work. But that's the idea. You define a common gateway, a common interface, and then you have different implementation of the same interface. And as long as you respect that interface, you have the same software can run on many different underlying hardwares. What would it happen instead without an ISA? Well, without an ISA, there would be no standard way for software to interact with hardware. Now, each processor then would require a specific software, making it much harder, not hardware, much harder, it's funny, much harder to develop software that can run on different hardware, therefore limiting portability and compatibility. I mean, think of this diagram that I draw here. Now we have a common interface, we have 3 different CPUs, the same software. If I remove this common interface, the same software has to choose which CPU to run on. So we have software for CPU 1, software 1, software for CPU 2, software 2, software for CPU 3, software 3. So now the software has to specialize itself for all these different hardwares. So now it is the burden of the programmer to do this specialization work that highly depends on the nature of the hardware. And this is not really that good, I would say. So that's the idea. Now, what is the difference between 32-bit and 64-bit? Now, in the context of Intel processors, there are different ISAs, of course. Nowadays, the most common ones that you will find are the x86, which defines a 32-bit hardware architecture, and the successive x86-64, which defines a 64-bit hardware architecture. So, of course, they are similar, they inherit many different things because one is the successor of the other. However, they also have a lot of differences. So, in this video, we will analyze some of them. Now let's go with the more obvious thing. Since we are talking about a 64-bit processor, well, a 64-bit processor can handle 64 bits of data at once, while a 32 processor can only handle 32 bits of data at once. So like the buses where bits run are just bigger and more bits can run at the same time and can be managed at the same time. So this is like general. Now, in a 32-bit processor, the address bus, of course, is 32 bits. This makes total sense. Now, how many things can we address with 32 bits? Well, this is just 2 to the 32 bytes, which in total is about 4 gigabytes of RAM. And actually, the space in reality is less because you also have like memory reserved for system use, for the kernel and things of the sort. So an actual application running on a 32-bit processor can typically address less than 4 gigabytes of RAM. Now, in a 64-bit processor instead, the address bus is 64-bit. Now, the cool thing to understand is that between 32 and 64, the growth is exponential in a way. But like for every bit, it is an exponential growth because every bit doubles the amount of space. This means that we're adding 32 bits, so we can imagine the growth is crazy. And indeed, the amount of addresses that we can address with 64-bit is 2 to the 64, which is 80.4 exabytes of memory. So theoretically, in a 64 hardware, we have 2 to the 64 bytes. However, in real system, we don't need this crazy amount of space, and so hardware designers and implementers, what they did is that they said, okay, theoretically this is what we can support, however, let's support a little bit less. Specifically, let's just use the lower 48 bits for addressing out of the 64 available. This makes it more efficient to implement all the hardware stuff. I mean, there must be some reasons for it. And we don't lose much space because even with 48 bits, we still have terabytes of RAM. So it's still very good for usage. Now, of course, another important thing of hardware architectures are registers, which are memory locations that sit close to the CPU, that are inside the CPU actually, and the CPU uses this memory location to perform computation, like adding numbers, like moving memories and stuff like that. So in the change from 32 to 64, some registers are extended to handle the 64 bits variation. For example, in 32-bit we have the register EAX, and in 64-bit we have the register RAX, so it's like R it stands for 64-bit. Some registers are new, such as the one that go from R8 to R15, which are general purpose. So even in terms of register, of course, there are different changes. And then we arrive at the objective of this video, which is to analyze the calling convention. Now, in 32-bit system, you do not have too many registers. You do not have too many general purpose registers. So the idea is that when people were to implement calling convention, were to implement function calling, they decided that arguments should be passed on the stack. So with the instruction push and pop, you have this memory in this region of memory. This is called the stack. So the first argument is push first onto the stack, followed by the second argument, the third, the fourth, and so on. So the memory use is the stack. Now in the 64-bit version instead, arguments are passed using registers. And there's a specific order like RDI, RSI, RDX, R6, R8, and R9, and things like that. So there is a specific order in which these registers are used. Now, why did they make this change? Well, because if you think about it, accessing data from the stack every time you call a function is more inefficient with respect to just using the registers. I mean, the registers are inside the CPU, so the CPU can quickly access their value. If instead we have to go through the stack, then we have to, fetch some area of memory. I mean, we have caches in the middle, so they can speed up things, but in general, if we have more general purpose registers, as it is the case for 64-bit systems, then we should make use of them also for calling conventions. So this discussion was very theoretical. Now let's see a practical example. And for this, here I brought two different programs that essentially do the same thing. So let's quickly analyze the program. So here we have two different functions, vulnerable and main. Vulnerable is vulnerable to a buffer overflow, so be careful with this code. It takes in input a pointer to a character, so character pointer. It defines an array of characters of 512 length, so technically in this buffer only 512 bytes should go there. However, then we call strcpy, strcpy, with the input writing into the buffer, and here we do not check whatsoever the length of this input. It means that even though theoretically here only 512 bytes would fit, here we could copy much more, causing a buffer overflow and different problems. However, the objective of this video is not to understand the buffer overflow exploitation. I made already some videos about that in the past. The objective of this video is to understand how function calling is implemented in 32 and 64-bit application. So notice this, we have this main function. It takes input from the outside environment, so this is typically from a terminal application. It checks if the amount of input is greater than 2, so if we pass at least 2 different arguments, and then it gives to the vulnerable function the second argument, because of course in C, arrays are indexed starting from 0. So this is the code. Let's compile it, let's run it, and of course nothing happened. Let's give it some output here. Okay, nothing happened again. But what we want to do now is just to debug it. So we don't really need to exploit it, we just need to debug it. And notice that here I compiled with the debugging symbol exactly for this reason. Now, first things first, let's get the different functions defined in this binary. Here we have a bunch of system function, and then we have the main and the vulnerable. We're interested in these two for different reasons. We're interested in analyzing how the main calls the vulnerable function, so what kind of calling convention it uses, what kind of underlying hardware architecture technique it uses to pass the arguments into vulnerable, and vice versa. We're interested in vulnerable to see how it reads the arguments from the main call. So let's start with main. I'm gonna set the disassembly flavor to Intel. So set disassembly flavor to Intel. This is just a different way of reading binary, of reading the assembly instruction, and then we can disassemble the main function. And here we get the code for the main function. Now, out of all this code, we are interested in the call that happens at 46, this instruction, call vulnerable. So call at this address, which is where the vulnerable function is defined. So this is how it actually calls the function, how it moves control flow from the main to the vulnerable. However, what about the arguments? How have the arguments been passed? Well, if we go an instruction before the call, what do we see? We see a push instruction. Now, push is an instruction that is used to operate the stack, and the stack is a memory region of the process that operates as a stack. So, using a LIFO policy, where LIFO stands for last in, first out. It means that the last element you're pushing on the stack is also the first one you're gonna get with the opposite instruction, which is pop. So you have push to put stuff into the stack, you have pop to remove stuff into the stack. And this LIFO policy is called like this because we have to imagine that the stack is something that, like, for example, here I put something on the stack, then I put something else, and I put something else, and I put something else. But then if I want to remove stuff, I cannot remove the first item I pushed, I have to remove everything else first. So the only element I can remove is the last one I pushed, then the second to last one, then the third to last one, and then finally the last one. So that's the idea. Now, to understand the assembly code, it's useful to compare it with the source code that we can read. So, for example, let's check if argc is greater than 1. Well, if we check into the code, we see that at instruction 29, we do a compare between the hard-coded value 0x1, which is of course 1, and a pointer in memory, so the region of memory that is pointed by the value of EAX. So that's the idea. Now, this instruction specifically, the word PTR with the square brackets EAX, it means use the EAX value as a pointer that points into memory and obtain the value in this particular location and compare it with 0x1. Now, since here we're comparing the variable argc, we can infer from this that the variable argc, that the pointer that contains the value of argc, is actually stored into EAX at this moment. Now, right after the compare, we have a jump less equal. So we're jumping only if the comparison gave a result less equal. And we jump at main 54. So we go main 54, this one. This is an op instruction, so it does nothing. And then essentially we exit the function and we do not call vulnerable. Because of course in this code, if argc is less than or equal to 1, we do not call vulnerable. We call vulnerable only if we are greater than 1. So only if this thing is not true. So let's now focus on the instructions that are executed right before the call to vulnerable. We start with this move. Now this move takes EAX, adds it at 0x4 and loads the memory of this thing into EAX itself. So we are modifying EAX. Now remember, initially EAX had the address of this variable. When we do plus 0x4, what is going on is that we're getting the address of this variable. And when we're loading it from the memory into the register, essentially, here we're taking the address of this array of pointers. Because arg of v, it is an array of pointer, so it points to different pointers. Pointer 1, pointer 2, pointer 3, and now we have the address of this thing. Perfect into EAX. Now the next thing is that we add to EAX 0x4. Why do we do that? We do that because we are not interested in the first pointer. Here we do not access argv of 0. Rather we access argv of 1. Therefore we have to go to the next pointer, and this pointer are 0x4 long because they are 4 bytes, which means that we have to do an add of EAX of 0x4. At this point, we actually can read the value of this pointer. So we do a move of, we read the value of this pointer and we put into EAX. So at this point, we have the value of this pointer. And what we do a sub of ESP. Now, when we do a sub of ESP, this means we take some space into the stack. So the stack was like this, and ESP points to the top of the stack. We want to increase this top so that the new top has some space here, so that the new ESP can point here essentially. And since the stack grown towards lower addresses, we do a subtraction. So we subtract, and this thing is like 12. So it's 12 bytes. And finally, we do push EAX. So now we put into the stack the value that we got from the argument. So now the argument has been passed into the stack, we call the vulnerable, and then we do an add ESP 0x10. So we are cleaning up the space used for the arguments for the variables. So that's the idea. So this is a calling convention in 32-bit application, and if we check, of course, if we do disassemble vulnerable, here we see, what do we see? Well, notice that this vulnerable is going to use the input in the str copy. So here we have the str copy, right? Now, in this case, what we have here, we have a push. So this is just used to prepare the stack for the local variables. And here, right before the call to the str copy function, if we check the code before, we have a push here and a second push here. And these two pushes represents the two different arguments that we give to the function strcopy. Indeed, let's put a breakpoint, vulnerable plus 59. Actually, let's do vulnerable plus 44. And then we do run with some input, a. So we say no to debug info d, whatever. So at this point, essentially, symbol vulnerable, we are at this point in time. So what are we really pushing into the stack? Well, we are pushing the value in memory that was obtained from this address. So EBP minus this thing. Now, if we check this value, this address essentially, so it's X, and then here we put EBP minus 0x12c. So this is a memory address. If we analyze the memory at this point, let's analyze it in terms of, I want just a word, so one word in hexadecimal. So this is the value that we get. If we analyze it as a string, we don't get much here. And of course, if you analyze it as a string, we don't get much because regardless, these arguments are pointers. And indeed, when we dereference the pointer, so when we are accessing the memory pointed by this pointer, we get AAA, which is the argument of our function. So essentially, the idea is that this push is taking things from the stack and is pushing them again for the new function call. So that's the idea. And then of course, in the next push, I expect that this is gonna be the pointer to the local buffer, which is empty. And so this is it for this first example. As we saw, so this is the example, essentially the arguments are passed into the stack using the operation push and pop. Most of the time we don't see a pop on the function that is being called because the function directly reads the value from the stack, but essentially that is the idea. So this is it for the 32-bit example, and now we can start the 64-bit example. The code is literally the same, it's just that now we omit the flag to build a 32-bit binary, which is this -m32. So how do we do that? Well, we just compile it as before, and we just debug it as before, example 64. So we say info functions, once again we have the main and vulnerable, we set the disassembly flavor to Intel, and we disassemble main as before. Disassemble main. So now look at the code, it's much shorter. And notice something in this code. Before the call to the vulnerable function, here we do not have any push or pop. The only push that we have is at the start of the function, because even in 64-bit application, the stack is still used for local variables. Like for local variables, the stack is a very good place to use. However, for calling convention, the stack is not used anymore. And what do we use instead? We use registers. And notice this, before the call to vulnerable, we put into the RDI register the value taken from racks. Now, what is this value? Well, if we analyze the pattern that we saw before, essentially the idea was that, okay, we read something from memory. This is the pointer to our array of pointers. Then we add a 0x8. Now, before it was add a 0x4, because each pointer was long 4 bytes. Now we want the second pointer of this array, and each pointer is long 8 bytes. So we need to add 8. And finally, we read the value at that position, which is the pointer we're interested in. And then we get this value, and we put into RDI. And then we call the vulnerable function. If we instead disassemble vulnerable, once again, let's zoom in with respect to the strcopy call. Before the call, do we have push or pop? No, we only have push at the start for the local variables. As usual, we actually have move into RSI and RDI. And how do we get this value? So, RSI is read from RDX, RDI is read from racks, and RDX and racks are handled before. So, RDX essentially is read from the stack, so we do RBP minus something. Now this thing, RBP minus something, was actually moved from RDI. And if you remember, RDI is what we put into the register before calling vulnerable. Here, we move racks into RDI. This means that to change arguments, they are using RDI, so to communicate the first argument of the vulnerable function. So it means that we go from this RDI to this RDI into this memory, and then this memory is put into RDX, and then RDX is put into RSI. So I believe that if I run the program with a string AAA, and I put a breakpoint here, and I get the value of RSI after this instruction, so actually in the 5th instruction, I should get the string AAA. So let's put a breakpoint here into vulnerable plus 50. I run with AAA. I do no debug info D. Here I did some wrong command, but at the end, when I analyze the memory of RSI using a string, I got my AAA input. So essentially, this proved that what I was thinking was true, is that in RSI, we have the second arguments. In RDI, we have the first argument, because in the code, the first argument is the buffer, the second argument is the input, which means that in 64-bit application, the arguments to the function are passed through registers. And indeed, in the RAX register, which is then passed to RDI, we're going to find the pointer to the buffer, to this buffer, essentially. So that's the idea. Now, just to play a little bit more with this thing. When you are analyzing this kind of program, let's say, for example, that here I was like, okay, let's disas main, here put disassembly flavor intel, disas main, essentially. So here I was saying this thing about 0x8. Let's change it to put, like, for example, 2. Here I expect a 0x10, but let's make sure that this is true. So I compile it, I debug it, I say set disassembly flavor intel. I mean, this I should just put into some long-term configuration, and then this as main. Look at that, RAX 0x10. So my guess turned out to be true. And in general, this approach is very useful when you want to understand complex things. You have to create a model of the complex thing, and then you have to play around with it. You have to understand how reality will change if you change some parameters of the model. Like in this case, for example, since here I was like, okay, we have to put the first element, we have to offset 8 bytes from the start. If I have to put the second element, now we have to offset 8 plus 8, which is 60 bytes from the start. In hexadecimal, this is 0x10. And this is it for this video. I hope it was fun. In this video we analyzed different coding convention between 32-bit and 64-bit application. This knowledge is extremely useful if you want to understand in-depth binary exploitation. Because if you want to, for example, exploit a 32-bit application, then when you want to call a function, you have to prepare the stack in a certain way. Instead, when you want to exploit a 64-bit application, when you want to call a function, you do not have to set the stack in a certain way, you have to set registers in a certain way. And for doing this, there are so-called ROP chains with ROP gadgets that essentially allow you to take pieces of the assembly code already present within the program and use them maliciously to set up the registers in such a way that you can then call different functions with the arguments that you want. And these techniques are used to do control flow hijacking and execute malicious and arbitrary code. Maybe in a future video I can showcase more on that. So this is it for this video. Share this video and this channel with like-minded people, and to the next video.